My PCB actuators are always the eye-catching part of my videos, but behind their unique motion there is a brain that is controlling their movements. So today we'll be talking in more detail about how I made this custom-made driver, which is also now for sale on my website. The goal for this project was to make an easy-to-use multifunctional controller for PCB actuators that is also packaged in the smallest footprint possible. To reach this target I had to go through multiple iterations, which helped me optimize the shape of the board, identify hardware failures, and improve the functionality of this driver. Version 1 was very simple as it only had an H bridge. The H of this bridge refers to the 4 switching transistors that control the current through the coil. My actuators are very low power, which means that I could use a fully integrated driver that also included a gate driver for the MOSFETs and some other internal protection features, and for this prototype I decided to use the smallest package that I could find, the PAM8016. This made the PCB super small, but from a functionality point of view it sucked because the user had to generate the input signals. It was also limited to a 5.5 volts maximum, so I changed my design to use the DRV8837. This could handle a maximum of 11 volts at 1.8 amps, making it capable of driving multiple actuators in parallel or in series. I decided to control this driver with a PIC 16LF18323 as it was the cheapest, the smallest, had an internal clock source, a small EEPROM block and 2 PWM modules. These PWM signals are generating the output waveforms, which are divided into different functions as indicated by these LEDs. As you can see here, the tactile switch is used to change the mode. The first one is the square wave function, which can drive the actuator differentially between 0.5 to 30 Hz in steps of 0.5. This can be adjusted by turning the potentiometer with a Phillips screwdriver. The software is basically reading its ADC value and turning it into an index. This index is used to get the timing value from a lookup table to linearize the steps. This frequency adjustment changes the speed of my PCB actuators. However, one can also use this to drive DC motors or other magnetic stuff. The next mode is called PWM mode, which drives the actuator more gently. To create the signal, software is driving a 20 kHz PWM signal and adjusts its duty cycle every 160 microseconds. So if you filter these pulses, they will form a triangular wave. The third function is called positional control. Here, the potentiometer will adjust the duty cycle of a 20 kHz PWM signal, which controls the magnetic field strength of the coil and vary its distance from the magnet. This mode is implemented twice for both magnetic polarities. I think this function is very handy for other applications, as I also used it to adjust the brightness of LED strip lights. I also did an annoying buzzing function which generates a square wave between 1.7 kHz to 16.8 kHz. The output is being driven differentially here, so you can also connect a piezo buzzer. The last function is external mode, which gives the user the ability to control the output via these two pins. I decided to put the input and output connectors on the backside, which was really a space saver. This outer edge grounded copper is just good practice for ESD protection, but the main reason that I did it is that the board just looked weird without it. This other chip here is the 3.3 volts regulator. I kind of had a big waste of time issue related to this part because I ordered the first batch with a 2.2 microfarad output capacitor. This was insufficient to supply the microcontroller's load and was creating some glitches, so I had to rework all the PCBs with a 22 microfarad capacitor. But at least the issue got fixed and the output is now smooth as butter. The final software feature I did was saving the mode in EEPROM, which remembers the function the user was in when powering on and off. Flash memory usually doesn't have long endurance, so you have to be very careful not to write too frequently in EEPROM. In fact, the software is only saving a new mode after being used for 5 minutes. To make sure that this doesn't fail in some way, I ran a test with 12 PCBs, having one set continuously on and the other being switched off every half a second. This ran for more than 280 hours and nothing bricked. I also made some 3D printed cases for this driver to make it more practical. This one is just a back-sided cover, then I have one that is totally enclosed, which is perfect if you just want to forget about it and leave it powered on for a very long time. And then I made the stacked version that makes my 12-layer PCB coil super compact. All the files for this project are open source and available on my GitHub. Everything else is explained on my website's datasheet. I hope that this board can help some of you get started with controlling PCB actuators. I have a lot of more content coming related to this tech, so make sure you are subscribed. And if you are looking for more frequent updates, I have also created a new shorts channel. So if you're into that kind of thing, please also check it out. Bye bye!